So here we go. What the plan here today is to finish this hands-on example to turn this little gravity packing thing into an odometer test and look at how it behaves a little bit, and then actually introduce the first level concept of bonding so we can make it into a solid, and then squeeze that, turn that into a UCF test. And then we're going to dive into fish. And we're going to begin with well, it's basically a pretty comprehensive lecture that then has hands-on examples that we're going to do. And I'm going to maybe have you guys repeat them over the next week, if you're, willing to do that. And so that's the plan for today. And we'll see how far we get. And then we're going to actually talk about bonded particle modeling. That's kind of the scary part for me, because I'm going to try to redo my entire lecture about bonded particle modeling. So we'll see what happens on that. All right. Okay, we got the big picture. Gravity pack, this is the thing we were playing with. Make a cloud of particles, let them fall down. Take those guys, do the thing that Ayat is doing right now, doing the odometer test on these propant beads. And so this is the plan to make this system right here. So let's go, and I'm going to go back to that example. Tutorials, gravity pack. So I'm going to fire up PFC2D. For those of you that have not run PFC, the PFC3D is almost identical to PFC2D. And so all the commands are the same. All the behavior is the same. So if you know how to work PFC2D, it will be trivial to also work PFC3D. And we're doing 2D because it's quicker and easier, and you can see things easier. In 3D, you have to spin things around, and you can't quite see things as clearly as the 2D. Okay. What do we got here? Let me look at my notes. So let's just run this to remember what we've got here. Look at the view. We have walls. We have balls. We created a cloud of them, and they're falling into the box. And I'm going to start this over. Hang on. Here we go. And let them fall. Not going to worry for a moment about those guys that are going out the sides. You can see those black things. Those are contact force chains. So those are particles bouncing against each other as they're falling and building up this force chain network, right? What's the key thing you see about the force chain network in terms of thickness?
The bottom one are higher.
Exactly. There's more load on the bottom of the mass because of the load on top. And is that, if we took the total force on the bottom wall, is that going to be equal to the weight of all the particles?
Yes, right? All the particles inside the box.
Correct. But what did we talk about? Remember the thing about the bin? Remember that story I talked about, the professor that had that guy with that big tube of steel, and he filled it with powder, and the guy was able to hang on it? What's the deal going on there?
The fraction.
Sorry?
The fraction.
Friction. Tell us more.
Uh,
The hint is in the force chains. So if we were to run this with zero friction, then all of the forces on the sidewalls would be directed normal to the wall. Because if there's no friction, you cannot build up a shear force on any of these particles. And so that then means that yes, all of the force, there will be no force carried by these sidewalls, and all the force will be on the bottom. So that has to equal the weight of all the particles. But if there's friction, some of the force is carried by the walls, and you can see that, all right? Look at these forces. They're not normal. They're pushing upwards. This here is the force acting on the particle. This is the orientation of the force. And so you can see that there is some force pushing upward, which means all the weight, some of it's going into the sidewalls. Okay. Does that make sense?
Yep.
You remember we talked about that? Okay, let's go back to this thing, get oriented again here. Oh, yeah. And this is, hold on, what are we generating here? Oh, okay, so here I was showing this ball distribute command, which lets you make a generalized size distribution of particles. And so you give a volume fraction of each chunk, and each chunk you tell it what size to be. We're not gonna do that. We're gonna just go back for our purposes of illustration back to the system we had before, which is even smaller. This was this ball generate command. Let's just see what happens here. This just generates this cloud of particles. Here it did 480 of them, and they're not overlapping. And we're turning on damping and gravity. And we're gonna solve this thing. Here we go, model solve, right? So if I put a pause here, just trying to remember everything we've done. So we generate the particles. Let's get rid of this other stuff. And let's make it real simple again. Let's go back to the simplest possible model. Right, model new, create a new model from scratch. Call in this fish function. We're going to use. Am I back on? My headphones cut out. Yes?
Oh yeah,
Yeah.
now we can
Yes.
hear
Yeah,
you.
okay. Model new, start a new model. Tell PFC to run in large strain. Set the C to the random number generator so that when we use it, when we generate these things randomly, we're always going to get the same answer. Give it a title. We have to make a domain. Here we're giving, say, all contacts that form, no matter what, have the linear contact model. And we're giving a normal stiffness, shear stiffness, friction coefficient. Now we generate a wall. That's a box with 4 sides. We delete the top side. Now we've got 3 sides. Generate a cloud of particles above it. Give them a density, because now they can come up with a mass. Set damping, local damping to a high value. 0.7 is what we typically use to make it behave quasi-statically. Turn on gravity. We actually put in a measurement circle to illustrate that in the center, and we can ask that thing to compute porosity, for example. Use the history mechanism here to get that porosity. That's what we were doing. So we create a measurement circle. Here, hold on. Let's not worry about all this for a minute. Let's just make sure we understand what we did here. So here's where we make the particles above the box, and just before we run the solve command, which will cycle until this equilibrium ratio is met. We're going to have a pause, which means it'll stop and wait for us. So there it is. There's our particles. Now I can say continue. Now they're going to fall in there nicely. build up the force chains. Cycling to 1e to the -5 ratio. And it's still readjusting slightly. Takes a long time for a sand pile to stabilize. We're going to find that when we build bonded systems, we're typically going to compress them at a specified pressure. And if you compress them at a pressure, they come to equilibrium very fast because you don't have this slight rearrangement occurring near the top. So there's our system. We also created a save file called gravitypack.p2save. Let me see if I can make that bigger. There we go. That was this command, model save, right? And then program return. So we're done. And then we wanted to talk about porosity with the measurement logic. So we're going to create this measurement circle at this location. So if I run that, it says measure 5 was created. If I use the measurement plot item, which is here, I can see that's where we're going to be measuring things. And we're not going to measure them until the pile is built up. So that's going to be okay. And then we're going to make a history. We're going to sample it every step. And what we want to do is do this command. We want to make a history of the porosity inside that measurement circle. And so to do that, we need to create a fish function. And what this fish function is going to do when it gets called, it's going to return the porosity of measurement sphere 5. And we created measurement sphere 5. We told it we wanted it to be numbered with an ID of 5. Okay. And the history mechanism then is going to go and sample this fish variable. Here's the fish variable name, porous 5. That's our function. And so that's what's going to happen there. So if we run it to that point, it created a history of porous 5, right? We also, up top here in line 24, are creating a history of the force acting on the bottom wall. And so we use the wall history command, and we're giving it a name, force on bottom. And here it is, total force in the y direction. On which wall? On the wall called MV bottom. Okay, so if we run this, now we're going to see, there it is, created history. And so if I say history list, those are all the histories being monitored. Force on bottom wall, porous 5, telling us what they are. Okay, everybody with me?
Yes.
Yes.
Okay,
Yeah.
excellent. Now let's just run this guy. And so they're falling. Remember, that's just a measurement circle. That's not a ball. So we're letting this thing settle. Let's just stop it now. At this point in the thing. At this point, you can see up here, we've taken 3,766 steps. Here's what our system looks like at this point. Let's look at those histories. Let's get rid of this one. So I use the history plot item, which is down here. It's called the history chart. Select that one. Here we see the histories that are available. Remember, we did history list. These are the histories available. And so let's just first look at the force on the bottom wall. So I'm going to say plus. And so there we go. If we turn off this other stuff. All right, turn that off. Turn this off. I just deleted that history, sorry. Let's make it again, history of contact force. That's what we want. There we go. Can change its color. If I select the series, there it is, the line, color red. And this is the force. I'm not going to screw around. We can put axes on here. We can label them, all of that kind of stuff. And so here we're seeing the force. It was high when they first were bouncing, and now it's rearranging. So this thing is going out. Let's look at it now as it's falling. You can see they're falling. Oh, now they're starting to build up. Here we go. There's the forces. So it's measuring the total force on this bottom wall, right? And eventually, at the time once it reaches static equilibrium, that force is going to be constant and not change anymore, right? Okay, so we get the idea. Now, what about the porosity? We now also have that history of the porosity. So let's go and add that to this thing. And what do you think is the porosity going to look like? And we're going to plot it on the same axis on versus steps. So we're going to have two plots here, force on bottom, and then we'll give a different color for porosity. What's going to happen to the porosity? What's the curve going to look like?
It's gonna decline.
It's going to decline until will it reach a stable value?
Yeah, yes. When it reaches static equilibrium and particles will not move anymore, or the balls basically.
All right. I agree. You guys agree? Makes sense?
Yes.
Yes.
I would think that when it pushes down, they're going to kind of like be bunching up, and then they're going to move back up, and they're going to slowly like rearrange and kind of get less dense. So let's add a new so actually in the same history, I'm also going to click porosity 5, which is that fish function. And so now it's also plotting porosity. But the problem here is these have different units in the y-axis. So I can't actually plot them directly on top of each other. So I'm going to have to make a separate plot and do that. And I think I can make two plots appear side by side in this interface. So let's try that. So I'll also show you this. I've selected here the history plot item. I can copy it and paste it and then make changes to it. So if I select it, I go up here, there's a copy, and then next to it is a paste. So now I've just duplicated it. So let's turn off the other one. And this one, I'm going to get rid of the force on bottom, hit the X, and I'm going to do porosity versus step. We see that. And it's doing what AI had said. It's getting less and less, and then it has stabilized at about 0.24. And let's see, I think I can split this view. I've never done this.
It's the next
Maybe
one.
it's this guy. It looks like a split through the middle. So split right and click on this. How the hell do I decide what to show here?
Yeah, it's on select content.
Oh, there you go. And I say what? I want to show a plot.
Data
Oh,
file or
plot
plots,
my
yeah.
view. Oh, but I lost this one. How do I get back? How do I get them
You
both?
can't show the same thing on both of them.
Oh, I see. Okay.
Yeah.
Oh, you cannot show the same thing. That would make sense. No, okay, of course you can't. So let's get rid of this. So that means I have to make a new plot. So over here,
Yes.
I'm going to click plot, give it the right finger and say new. And I'm going to say my porosity. So this is a whole new plot window. It has no plot items in it. I'm only going to put in the porosity plot item. So I go, I want to do the, not the plot, the history plot item. Here we go, history chart. And now I'm going to choose porosity. There it is. That's good so far. And then I'm going to go back. See over here, these are my plots. I'm going to go back, double click on my view. Now I'm going to get rid of that porosity from there, delete it, turn on that one. And now I'm going to split the window, I think.
Yes. Yes.
Split right, click, select content, open my no, that's not it. Select content, plots.
Plots.
My porosity. Oh, we got it. Okay. Oh, yeah, can we put these things above each other?
Yes.
Oh my God. Can I do that? So I say split above. Oh, this
Now
is
you
nuts.
have 3.
Now I have 3. Okay,
Yeah,
wait. So I'm
okay.
going to do this. So I'm in this one. Now can I split that? How do I split? Oh, select
Yeah,
content
yeah.
up here, plots. So I've got my view. Oh my
Yeah.
God, this is so cool. Okay. So here we go. We can see what it's doing, right? It eventually is, the weight is stabilizing and the porosity is stabilizing, right? And the view, yeah, and then we could actually have another view, right? And we could show the particles and stuff, right? Okay. You with
And
me?
you can see
Yeah.
that they didn't reach the static point at the same exact point, like the porosity reaches
Like
the
right here.
final, yeah.
Yeah. So why is that?
Uh, I think because the particles were like not moving anymore, but they still have some kinetic energy to dissipate.
Yeah, I think that's it. I haven't thought about this. I mean, I think basically they reach a kind of packed state and they're not really moving much relative to each other. So once
Yeah.
they don't do that, this doesn't change hardly, but they're still not 100%. They're still slightly readjusting and moving around. So that's having a negligible effect on the porosity, but it's still having a noticeable effect on as that total force has to build up. Yeah, that's a good that's an interesting thing. And I bet if we zoomed in on this one and looked more closely, this porosity is probably changing, but not at this scale. See if we can do that. How do we do that? History,
Oh, you can
y-axis.
just zoom in like with your mouse.
I can zoom in. What do I do?
Like
What button?
you
Oh,
left click and drag
okay, wait, hold on. So I wait,
on
do I
on
do
the figure. On the
I
figure
left
itself? Yeah. And now you can just left click and drag on the figure itself.
so here
Yeah.
on
Wherever you
this,
want. Yeah.
I left click. Oh, left click.
Yes. And drag.
Okay, that's not doing it. Maybe I have to have the
Oh,
pointer selected, but then
yes.
it keeps going up there. Um,
Yeah, like
yeah,
that.
that's what it did up here. How do I? Yeah, okay. I'm sorry. I'm not. Let's not mess around. Um, let's just get rid of that one. Left. This now it might work. Left click and drag. Boom. Yeah, it's too sophisticated. I'm just gonna go here and say y-axis, and I can set minimum and maximum. So the
Yeah.
maximum will be 0.25 instead of. Oh, and there we go. Make the maximum even lower. So you can see it's still readjusting itself because every time that thing slightly adjusts, but you can see it's just doing it at a very negligible level. Okay. All right, let's do one more thing that we can point out with this example. So let me think here. Okay, how many particles do we have in this thing? What I want to do is after this has settled, we're going to define like 3 layers of particles, and we're going to color them differently. Okay, this is for this deal. This is the work I'm done for this oil company. They want to drop in color layers of sand, because then they want to push this thing and they want to see the deformation field, right? So let's see if we can do that. The ideal way to do that would be to make a cloud of particles and color them a certain thing and let them fall and settle, and then make another cloud of different colored particles and let them settle. Instead of that, to make it go faster, what I did for them and what we're going to do is just make one cloud of particles without any color, let them settle, and once they've settled and they're not moving anymore, now let's just define groups of particles. We talked about grouping. Every particle can be a part of different groups. And once we make a particle part of different groups, we can use the ball plot item and say we want to color it by group. And then we should be able to see the different layers. Okay, so let's see if we can write a function. It doesn't have to be big. Let's see. Just a second here. Yeah, okay. Let's see if we can do this. So let's go to this thing. I want to make maybe a little bit more particles so that we can, no, we don't have to make a little more. Let's just do this. And I just have to bear with it here for a second. Let this thing run and come to equilibrium. Contact force change, there we go. Get rid of that measurement. Just started cleaning things up here. There we go. Looking at this thing. Balls, walls, contact force chains, member, axes. Can make it bigger, smaller. I can make the axes always stay at the lower left, no matter where this is. They're at the lower left, or I can go to the axes plot item and I can say fixed and I could uncheck it. And now it's at the 0, 0 point. This was where we built our box, that's 0, 0. Okay. Enough of that. Let's put this back here. Turn that off. Okay. And now we also have a save file. So we'll be able to just restore that thing and do stuff as we try to write our functions here, okay? Okay, so we're going to make a new data file that's going to restore this state, and it's going to have to do some stuff here to assign balls to groups, first of all, okay? So I'm going to say file up top left, new data file, and I'm going to call this make layers dot p2 that. So here's the make layers. It's over here too. It's a data file, and it should be in the directory. There it is. There's a whole new file got created. Has nothing in it so far. Okay, and I'm going to always do program return. That's going to go at the end. And now I'm going to restore. So the command is model restore, and now I need to give it the name of the file. And that file is right here, gravitypack.p2save. So gravitypack.p2save. And that should correspond with the name at this thing. When I did gravity pack, I saved it. There you go. That's why it has that name. Okay, so let's see if this works. Remember, you do everything step by step. So I'm going to run this. Ooh, looks good. It said down here, model restore, and it told me when it restores when that file was made and all kinds of other stuff. And now we're just sitting here, PFC Command Genie. And if I look at it, there we go. Okay, let's get rid of this porosity. There we go, just that view. So make layers. So what are we going to do here? We're going to do a ball group command. And let's just call it layer A. Okay. Now, if I just do this, boom, group layer A assigned to 480 balls. So every single ball has a group label called layer A. So we can look at that. Here's the ball plot item, and I can say down here, color by text value group. And there we go. Let's get rid of this wall thing. Let's just make the wall. There we go. So now it doesn't have as much stuff on it. So the default slot is called layer A. And if I go more in here, ball group, and where I says color options, there we go. That's the only thing. So I can turn them on, turn them off. There's not that. It's a pretty simple thing. They all are part of that group. Let's just go quickly, just so that we remember this stuff. This is what we talked about, the grouping stuff. Let's look through that again. Group logic, right? Here's the idea. Here's a ball. It has all this information associated, and it basically, think of it as like actually writing it down like this. And there's a slot, and it's the slot. This particular one you always get, and it's called the default slot. And you can put a name in there. So in this case, left side, we just put a name in the default slot. That was layer A. Default, layer A. Okay, because we gave the command ball group layer A, and we didn't tell it a slot name. We didn't do anything. We just said, boom, do it. So then it just said, okay, I'm going to put it in the default slot. Okay. But then we can also, and there's the example, ball group left side. Now there's this range here. Why am I doing a range with the ball group command? What happened? The default slot. Not everybody got affected. Only some of the balls had that tag put on them. Why is that?
Oh, because we selected the range, right?
Exactly. So remember, the way that this range logic works is that it's like a filter. It says, whatever this is here, I want you to filter all of these balls. I want you to filter this command, whatever the command is. This applies to any command. So this is the ball group command, but I only want you to apply it to balls that satisfy this criteria. Okay. And so that's why when I give the command, the default slot gets the word left side in it, but the other guys are unaffected. And so the plot item is kind of nice over here. It lets us, if there's some that are not affected, they're gonna be called none. Okay, you with me?
Yes.
So
Yes.
let's try to do that for our system. Ball group layer. Let's say range, position Y. And in this system, if we turn back on the axes, that's 0, 0. And this is a 2 by 2 box. So this is -2. So let's just screw around here. Let's see if we can go from -2 to -1.8. And we should get a layer at the bottom. Okay, so let's try it. Position Y. And I'm going to make this a little bit bigger. Editor. Size 16. Apply. There, might be easier for you guys to say. So we go from the minimum Y to the maximum. So I'm going to say -2 to -1.8. Let's see what happens. I'm going to run that. So it looks like it might have worked because it says the layer A was assigned only to 76 balls. And there's 480. So now let's look at them with the view. Ooh, I think we might have nailed it here, right? So there we go. Default is red, and these guys are none. Nothing happened. Command didn't apply to them. Okay? So let's make 3 layers. Okay? So ball group. Let's call this thing layer bottom. Let's run that. Make sure this is going to be called layer bottom. There it is, layer bottom. Let's do layer bottom, layer middle, and layer top. So layer bottom, and let's make layer bottom go a little higher. And then this will go from -1.6. Let's say -1. Let's look at what this is. Let's call it layer middle. Bottom middle, and then there still should be some none left over. Look at it. Oh, here we go. Bottom, middle, and these guys are still, nothing has happened to them. Okay. So let's put those top as the next thing. Layer, bottom, middle, top. Right? And let's make this go from the -1. Let's just make it go even higher to make sure we capture everybody. So now I run it and I look. There we go. There's no more nuns. Right? So every ball now has a particular thing sitting in its think of it as a little text string. Layer middle, layer bottom, layer top. Now, this is okay for really simple models. We can use this default thing, but we might want to have multiple things here. We might want to say a ball is part of a certain layer, It's also part of a certain material type. It's also part of a certain something else. So we don't want to use default. We want to actually control the name of this slot. And so that's this idea. Notice, look here. We would like to, in this case, we actually can put a name of a slot. So we can say, in the slot called layer, what word are we going to put there? And in the slot called material, what word are we going to put there? So for this thing, layer seems to be a good name. Let's make a slot now. So we're going to say ball group layer, and I'm not sure what the command is, syntax. So I'm going to hit F1, ball group. You give the name of the group, and then you can say slot. So watch this, ball group layer bottom, slot layer, return. And well, let's just look at this. Boom. Layer equal bottom, none. These guys are none. But this is kind of weird because the layer is actually called layer bottom. Well, now the slot's called layer. So I don't need to say, make the word be layer bottom. I should just call it bottom. So here we go. The name is going to be bottom in the slot called layer. So here we go. So there we go. In the slot called layer, it's bottom. So let's use that slot for all three of them. Right? So all I need to do is add the slot layer command. Well, not quite. Let's do this first. And now we're going to get rid of that word. Right? And now we should get all of them. Now look at this. Here we go. Ball group. Layer is bottom, middle, top. But this is also kind of awkward. I don't want to frickin' have it say layer every time. Wouldn't it be better if it just said ball group layer up here and then it just said bottom, middle, top? It'd be much cleaner. So I'm going to go to that ball plot item, and right now it says color by group. But when I go to slot here, see it says slot. So now it's just showing any possible slot. I want to say layer slot. So there's a slot called layer. Here we go. Ball group layer. End, bottom, middle, top. Okay. So this is going to allow us to do all sorts of things, this group logic. Okay. And this is a key thing we're always going to be using in PFC. Okay. Is everybody with me?
Yeah.
Yes.
Yeah, yeah.
Yes.
Okay. Now I'm going to blow your mind. Okay. So far, this kind of makes sense, right? So what I just did here, again, is I let this thing settle, and then I defined these layers. And so what I just did is this, right? I just gave it, different names, if you will, assign them different groups, and then I can go and change their colors. And I can now watch what they're going to do, right? Because the group that I designate a ball with never changes unless I change it later. So, so far so good. Now, here's my challenge to you. So, what if, like in this tectonic world, what if you wanted to say, so this just actually corresponded with their physical test that this oil company does in their lab. They take colored sand and they put a certain color, and then they put another color in, and they shake this too to vibrate it so it gets nice and flat between layers. And then they can look at all this cool stuff, right? But the material they have it's just a granular material. Pretty limiting thing, because real rock that they're looking at that's doing folding and thrust faulting and all this stuff is usually not just dry sand. Usually there's like a layer of sandstone, and then there might be a sand layer, and then there might be a clay layer. And so what if they wanted to do that? So that would be really hard to do, right, physically in the laboratory. I guess in principle you could, right? You could put some sand in. I'm not even sure how you could do it. You'd have to put sand in there that had some kind of cementing agent with it and then somehow activate the cement after it's been put in there maybe or something. I'm not aware that anybody does that. But with the model, of course, we could do that. So what if we want to now go and say, I want to take all the balls that have contacts between two balls that are in a certain layer, and those contacts, I want to bond them to now make that into a solid like a rock. Because in the PFC world, all the action happens at contacts. So if you have a packing of particles, all of the material behavior, because these are rigid, really everything is being assigned to the contacts. And so what we can do here, let me just make this 100% clear here. Let me share the screen in this other world here. Share screen. Okay. And can you see this other screen now? Can you see my notepad?
Yes, we can see that.
Yes.
The hello world. Remember that? Okay. Here we go. This is a key thing in the world of bonded particle modeling that all sorts of people are doing nowadays. So again, let's say I have to make my electric pencil become electric. It has to turn on. Okay. So if we have a packing of particles, and let's make it simple because I can draw this better. Let's say this is our packed system. Let's say let's make 5 of these just to be clear. So these are all just touching. And now conceptually, we want to say here and here, this is going to be a rock, like a sandstone. And this part down here, which might keep going for a long time, is going to be dry sand. Okay. So what could we do? We could make these guys be a group called sandstone, right? We've been calling things like, late middle or something. And now we have to talk about the contacts. So we could say, oh, if you are a contact here, which means here I am, I'm a contact. This guy on that side is called rock. And this guy on that side also has a group called rock. Remember, because this contact is between a ball, that's a rock ball, and a rock ball. So I could find just those contacts. So if I looked at every single contact in the model, the only ones that are between two rock balls are those 5. Makes sense?
Yes.
Yes.
Okay. Now there's going to be an other. Let's just, to make it even simpler, let's call this group rock 2. Yeah. Call this rock 2. So let's say that everybody else in here that doesn't have an X is a group called rock 2. And everybody with the X is a group called rock. So let's not worry about sandstone. Okay. And so how many possibilities, how many different types of contacts are there going to be in this system? One type of contact is this one. It's where both the guys on each side are both called rock. What's another possibility?
rock 2.
Exactly. There's going to be another. So rock 2, I'll draw those contacts as squares. And that's going to be these guys. And there's going to be those guys up here. So rock, it looks like I drew it like that. There's going to be rock 2, and I drew that as a square. Okay, and then is there any other possibility?
Rock
I
2,
don't
rock
have-
2.
Yeah, boom. There you go. Rock 2, and I don't know. Let's draw these as triangles. And I won't draw them all. Here we go. Are there any other possibilities in this entire world? I'm going to say the entire world, all the balls are part of a group, and they're either part of the rock group or they're part of the rock 2 group. Are there any other possible combinations? Let's make a little matrix of possible things. There's rock and there's rock 2. And over here, there's rock and rock 2. What I'm showing here is this is going to be one side of the contact, the group name of it. And this is going to be the other side. There's always just two possibilities. So here we go. This is rock. There's rock 2. There's also rock 2, and there's rock 2. So because there's only two groups, all the combinations of between the groups is delineated by this table. And it's symmetrical, and there's a R2R and RR2. We're going to, for our purposes, going to consider them to be the same thing. So that means there are 3 possibilities. Are you with me? Make sense?
Yes.
Yeah.
Well, I have a question that should we take the rock and the wall into consideration?
Really good point. If there's a wall, let's say there's a wall just there. Now those are contacts we haven't considered yet. And that would be a different type of contact, correct? And so now there would be, you could think of it as, think of a contact as always between two things. One of them's on one side and one of them's on the other side. It's like thing 1 and thing 2. And so, yes, these would be, if we call this thing, let's call this thing let's just call this thing a wall. Now this table gets extended, right? Wall. And so now you're going to have wall rock 1, wall rock 2, wall, right? R2 wall, R wall. These are symmetric here, so we're not going to worry about those. So now you have 6 possibilities, right? You with me?
Yes.
Okay. So what we would want to do then, if we wanted to build this model, for the time being, let's pretend there's no walls. If we wanted to build a layer that we call rock and a layer when everybody else is called rock 2, using this classification here, we could give different properties to all 3 of these types of contacts. So the rock 2 guys are going to be inside of this rock 2 region. And the rock are inside of that rock region. And there's interface here between the 2 regions, which is this guy. Okay. Are you with me?
Yes.
Okay.
Yes.
So that means if I draw this like a different way and just draw it as a crude box and say, look, here we go. This is my rock. And this part is rock 2 and this part is rock 2. Like if this was a continuum, I clearly can identify now 2 regions plus an interface between those regions, right? In this case, there's region R2, region rock, region R2, and then there's an interface between them. And what we've done is taken this thing and filled it up with particles. And so now it's only the contacts. So we have to classify the contacts based on this information here about who's on both sides. And so the contacts that are between these two, we're going to think of those as interface contacts. They're going to get different properties than the guys inside of rock or the guys inside of rock 2. Like maybe this rock layer is really strong, so they have high strength, but maybe this rock 2 is not strong, so it has lower strength. And then maybe the interface is really weird and complicated, and it like doesn't even have bonding. It's just a granular type of frictional interface. Okay. Okay, are you with me?
Yes.
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 Okay. This is actually a thing people do in more sophisticated bonded particle models. They take a rock and they fill this up with a very large number of packed together small particles, and then they superimpose on that different things. Like in this case, we did the layers, right? We say, oh, here we go. This is layer 1, this is layer 2, this is layer 3. There's going to be properties inside this layer, properties inside of this, properties inside of this. And then there's also going to be different properties at the interfaces. This is what we've just talked about. You might also go and do a super cool thing and you say, well, that's a big rock, but I want it to be like a granite. So I'm going to go and define some kind of crazy thing like this. So I'm going to call this a grain. And this grain structure, it might be some idealized structure like polygons that fill space, or it might even be a scan of an actual cross-section of granite where you look at you differentiate the mineral types based on color in the scan. And then you could map that onto this thing. And now what you end up doing is say, oh, all the particles, all the contacts that are between, so you group the particles based on which one of these regions they lie in. Now they're all different colors. And then you say guys of the same color, that has properties of grain 1. Guys between grain 1 and grain 4, that's that interface. They might have different properties. Are you with me?
Yeah.
Yes.
Okay. This is like so cool. Now we're going to continue this, okay, because you're seeing where we're eventually going. I'm trying to give you this idea. But look at this. I got to show you this. And I got to find it. Just a minute. And I might not find it on the first try. Wait, I know where it is. Hold on, just talk amongst yourselves. Just a minute here. I will find this in my weird world here of trying to store all this stuff. PFC course, there it is. New material. If we're lucky, it's in here. It is. Here's an example of this. This is a recent PhD work of Chang-Di He. He was also at University of Utah.
We're not
No,
seeing.
we can't see that.
Oh, thank you. Hold on. Hold on. Thanks for telling me. Stop sharing. Where do I stop sharing? Come on. Share. I don't have high enough knowledge to figure out how to run this damn thing. Come on. This is now is someone supposed to make the joke, how many PhDs does it take to run a PowerPoint meeting? Stop presenting. There. And now I need to start presenting. Share. Look at this. Now can you see? Yes? No?
Yes.
Excellent. Okay. Look at this. I think just the picture might give you the everything. I love these pictures. So this is work by Cheng-Di He, just like Ayad. He's also at University of Utah. He just finished his PhD. He did a whole bunch of work with PFC. And what did he do? He took these scans of granite. This is probably 5 millimeter across, and this is the grain structure of granite. He did all this image processing to pull out the three mineral, in this case, three mineral types, feldspar, quartz, and mica. And you can conceptually, and then he had a dense packing of particles, and then you essentially lay this on top and you find the colors, right? So if we zoom into this a little more, you can see it's going to look like this, right? So there's my colors, and we zoom in, and then this is grouping. So he made 3 groups in the slot called grain type. And in that grain type, he either put the word mica, quartz, or feldspar, and then he's using the plot item of the group to show which group they're in. You with me so far?
Yeah.
Okay. And then he classified all the contacts. And in this case, you can think of it, it's a 3x3 matrix, feldspar, quartz, mica on the column, feldspar, quartz, mica on the row, and then there's all the combinations. And in this case, there's 6 combinations. So now he's going to have contacts that are between 2 black guys, and they're going to get a certain set of properties that relate to mica and the quartz and feldspar, and then he's going to have these interfaces. Okay. And so this is what he did. He did this in 2D, but then he did a whole bunch of stuff actually in 3D. It's quite crazy because these models, this model here, if you think carefully about it, because for a bonded particle model of quartz, depending on what contact model you use, it might have 18 properties just to describe the quartz. And so that means you've got 18 plus 18 plus 18, and then plus all these different types of interfaces, right? And so you'd get these, there can be like 144 different properties that have to go into this model. It's a grain scale model. Those properties exist. He then did an extensive literature survey to say, what's our knowledge of just pure quartz? And what's our knowledge of the properties of quartz? People have done they've done different like atomic force microscopy, stuff like this to get the Young's modulus of a piece of quartz, right? And so there's data about that, sort of. And then there's, what about the interface between a quartz and a mica, right? And there's very little data on that. But nonetheless, this is the idea, right? This is the grand dream. If you could actually map in 3D the actual 3-dimensional arrangement of the minerals, and if you could then put in the property of each mineral and each mineral interface, this would be like the sort of super great fine scale. We call these grain scale models, right? And that's what he did. And returning to this, so he came to a year ago to my PFC course in Minneapolis. I'm working with him in the IEP. I was, and he shows up and he says after the first morning's lecture, and he says, Dr. Potyondy, I have a gift for you. And I'm like, oh, wow, you didn't have to do that. That's really nice of you. And he says, could I give it to you? And I say, yes. And so he gives me this. He took a bunch of little beads. These are just colored beads. You can see the length scale. There I am holding it. There he is. And he colored, well, you get the whole idea, right? He made this and it represents all this different geotechnical stuff by using the colored beads, right? And of course, I think he was losing his mind, right? Because he had spent the last 3 years doing this, right? So then he went and started actually physically doing it with beads, right? So this is the idea. This is the type of stuff people are doing. This is at a high level. It's kind of the stuff you're always doing with these discrete models. You're giving different properties to different regions. And now if you start bonding these things, now you have a wealth of properties, and many of the properties you don't even know. So this is like science stuff, right? You say, well, if we assume that the mica, we kind of know from the literature it has a modulus between this and that, then we can start, posing questions about what would changes in some of those things, how would they affect the response of the real material, right? And you do that by making models. And the models are never perfect, and they're not exactly the real material, but if you make one model and you gain some confidence that it's pretty much making sense, then you can at least compare all the variations to that model itself. So you can say, here's my model with these values, and it gives me this response, UCS of this. What if I only change the modulus of a certain one of the minerals? What effect does that have? Oh, that has a 20% effect, or that has a 0.1% effect, right? So this is also a use of models. This is often what we use models for in geotechnical and rock mechanics, because the systems are very complex, and we often, even if we knew all the physics, we still often cannot get the properties of such things. And so our models need to be used in this oftentimes more sort of scientific speculative comparison way. And then the last thing, see, I wish you guys were at the course, because like I went crazy when he gave me this thing. And so I ran outside. So pretend you were at Itasca. You come visit me. I'm going to show you around our cool little office. And I'm going to go to the wall and I'm going to say, look at this. Let's zoom in on this thing. This is hanging on our wall at Itasca. This crazy thing here. Okay. And you can, whoops, you can see the scale, right, of how big it is. And so, first of all, you say, what the hell is that? And who did it? So the first thing you say is, who did it? And I say, a guy named Peter Kundal. And if you're a discrete element person, you say, oh, he's the guy who developed discrete elements with his seminal paper in 1979. And so when Peter Kundal retired, he spent most of his career as an adjunct professor at University of Minnesota, and working, though, mostly for Itasca. And so when he retired about 15, maybe 20 years ago now, he started painting. And so this is actually a oil painting. I think it's oil. And I think it's like super cool. So what the hell is this painting? It's got all this crazy stuff. This is the Itasca logo. Okay. And there's like this river coming out of it. Okay. And I don't know if I told you this. I may have already given you that story about Itasca. The name Itasca, the origins of the name mean true source. And so we like to make jokes that Itasca is the true source of geotechnical modeling. And so here it is, the true source Itasca. Here it comes, the river of knowledge. And look at, there's all this crazy stuff here. In this river, there are polyhedral blocks. Okay, so you could say, oh, that's like a crazy 3-deck model with like fluid interaction and stuff, and they're floating. Here's like a bunch of balls modeling a slope, right? Here's an open pit mine. Here's a stress analysis of distribution around a hole, right? Here's a tunnel. I mean, all this stuff, right? So, it's obviously very similar to this thing, right? That's why I thought, oh, look at that. But so, okay, there's my stuff. Thought that was like very interesting. All right, let's go back. So with that big thing, does this make sense? Make a little more sense now where we're at, where we're going?
Yes.
Bottom,
Yes,
middle,
yes.
top. Okay. So the next step in this system is not to just identify and color the balls, but now we need to do stuff with the contacts, right? We need to classify the contacts. Okay. And so we can also assign group names to contacts. Just like we can say a ball, you have a slot called layer, and you know, you live there, right? So that's this idea, right? Here's a ball data, and it has a slot called layer, called material. Well, we can make a contact and give it group, and so this would be a contact data, and we can have a slot. Okay. So let's go and just do it here instead of on that other thing. So I'm going to change this. No fill, line, black. Okay, it's going to take me longer to do it, this klutzy thing in PowerPoint. Let me jump back to the sharing of the screen. Start broadcast. And do we got it? There we go. Okay. So you can see this, you can see the handwriting screen, right? Can you? Yeah.
Yeah.
Yes, we
Okay.
can.
So here's our system. And let's just, for illustration, let's go and conceptually do this. Lower, upper, lower, upper. We're going to make a collection of layers, and we're going to make the balls in here part of group L, and the balls in here part of group U. Okay. And so then if we draw our little possible combinations table, there's going to be 3 combinations. Sorry, U. There we go. These 2 are the same. So there we go. There's 3 possibilities. Are you with me?
Yes.
Yes.
Okay, 3 possibilities for classifying the contacts. Okay. And so like in this case, for this simple model, this would be U. These balls would be U. These are the balls now, not the contacts. L, U, L. Okay. And then we're going to find the contacts. There's going to be 3. Let's make a slot. So here's contact data. And we're going to make a slot. And I'm going to call it, the slot's going to be called the pair. Pair. Like 2 things. Pair means 2 things. And then we're going to put the words. They're either going to be, we're going to put the word LU, LL, or UU. And so we're going to find, like this contact right there is going to, in its slot, it's going to say LU. And this contact here, in its slot, is going to say LL. And this guy, here's all the possibilities, is going to say UU. You with me?
Yeah.
Okay, we're going to classify all of them. And we're going to do that by using the concept of grouping again. And then we're going to use the plot item because we can take the contact plot item now, which shows us all this stuff about contacts. And we can say color by group. And then we should get a plot up there, and it's going to have different colors of contacts, and they're going to be labeled with these labels. And of course, once we have that, then we can move on and assign different properties based on what your label is here, what group you're in. Okay, see the big picture?
Yeah.
Yes.
Yes.
Yes. Okay, awesome. And then we're going to take a break here. All we're going to do here now is see if we can get those assignments of these things. So I need to take my time, turn this thing off. Let's see. Stop presenting. Start presenting here. Got it. Can you see the model now?
Yeah.
Yes.
Okay, cool. So let's try and make, let me go to this group thing and I'm going to turn off. So here, ball, group, slot, layer, color option, bottom, middle, top. Let's turn off middle. There we go. Let's turn off top. Now we're just seeing the guys that are bottom. And let's see if we can find the contacts and label them that are between the blue guys. Okay. And so the first thing before we do anything else is we want to show the contacts. How do we show contacts on a PFC model? What do we do? To show anything in a PFC model, what do? We use a concept of a plot item, of a view, like a plot, we call it, right? So
Yes.
there's
So
there's
Yeah.
Add the plot.
sorry.
Add the plot items.
Yeah, beautiful. So there's a plot item called contact plus, and I gotta find it. There's a ball stuff here, some of their contact. Boom. This is called the contact plot item, right? Zoom in again a little. Here we go, right there. Contact, and I can say shape cylinder, or I could say shape sphere. Now it's just drawing this. Okay, and so this is showing all contacts in the model, right? If I go back to the balls and I don't show their group, I just show everybody as yellow. There we go. Those are all the contacts. Okay. And there's no grouping assigned with them right now. And as Young King pointed out, there's different types. There's also wall here. We're not going to worry about that for our system. Okay. And remember, we can look at the types of contacts based on if they're ball or ball facet or things. We can see that too with the ball plot item. We say color by new, the heck do I do? Color by. No, it's not the ball plot item. It's the contact plot item. And now I want to show contact type. There we go. Ball is red and ball facet is this pink, right? That's what we would have expected. Okay, so we're not going to worry about the ball facet ones right now. Okay, so we're going to go back up to contact and we're going to say color by group. We should see they're all none. Got it? Group. They're all none because we haven't given any grouping assignments. So let's go back. Let's turn back on the ball plot item and color by group. Our goal is to make these red ones become some other color, be part of a group, and not do anything with these because that's a different thing. We just want the blue guys. Okay. So in make layers, I do exactly the same concept. I'm going to say contact, group, and let's do the, oh, wait. Before we do that, let's remember the model I talked about was B. Let's get rid of middle. It was B and L. And we weren't calling it. We weren't calling it layer. We were calling it pair. No, wait, sorry. We are still just working with balls. Let's just do this first. Let's get this set up. I want to make those layers and call them B and L. So turn off the contacts. Ball group layers. Here we go. B and L. We still got a bunch of nuns in there. So let's go and make it so that there's like 4 different layers, let's say. So here, just got to change these things. So -2 to -1.6, -1.6 to -1.2. Let's just get this all the way across. So BL, B minus, go from -1.2 to minus what? Let's go 0.8, and then this upper one, -0.8 to some high number. Let's see what happens here. Group assignment, view. Cool. There we go. Bottom is green, L. So bottom, lower, lower, upper. Saying on, that's not correspond. Let's just change those numbers to lower. And it wasn't LB, it was lower and upper. There, now I might have what I want. There we go. Lower, lower, upper, lower, upper. With me?
Yes.
Yes.
Okay. So now we want to look at we want to get the contacts, these suckers here that are between the guys called lower. So we're going to identify the contacts that are here. We're also going to identify the contacts between those guys because they're also between lower, lower. Okay. So go back. Now, contact. So I'm going to be putting a label in the contact world, and I'm going to say the pair, I want to get lower. I'm going to call it lower, lower, and I'm going to put it in a slot called pair. So if I do this, it's going to apply. It's going to put all contacts, because I have no range. It's going to do all contacts are going to have this in the slot called pair are going to have LL. Let's see if that worked. Boom. Group LL assigned to 1046 contacts. Let's see. Let's turn on the contact any. Here we go. Contact group pair is LL. But let's use the slot. We don't want to say this stupid pair equals. Let's make it say contact group pair, and everybody should be LL. So go to here, contact plot item, color by group, slot. We want to use the slot called pair. There. Contact group pair, LL. So everybody now is part of that group. But we only want to get, remember, these guys between the blues to be part of that group. So we have to use a range. So we're going to say, I want to make the word LL go into everybody's pair slot, only the ones between those two. So how do I identify that? Well, think about it. There's going to be a special range capability here where you're going to basically say, I want to get the range of contacts that have a ball on one side that has the name L in it and a ball on the other that also has the name L in it. So this is going to look like this. Range group L. So that's one side. One side is a ball that has group L and match 2. What's this saying? Remember, every contact is only between and always between two things. And in this model, it's either between a ball and a ball or a ball and a facet. And what this is saying, this syntax here, is it's saying if the guy, in this case the ball, if the ball on the left side, and this is not quite right, range group L in the slot called layer, there we go. So if the thing on one side has a slot called layer, and if that slot has the word L in it, and if it matches on both sides, so actually both sides have to have L. So this should do the trick. Let's see. Let's run it. So group LL assigned 2. This is less, only 584. So let's look at it. Come on, here we go. And ball group layer, contact group pair. Now slot pair, color opt, none. Turn off the none. Let's make the none be yellow so it stands some other color. Here we go. So let's see if this is right. So there's only, in that group pair, it's either LL or it's none because we haven't done it. So I think we got it because every guy that's an LL contact is between blue. And every other one is still yellow. So what we've just done now is identified the contacts in the layer called between guys that are in layer LL. Everybody following?
Yes.
Yes. Yes.
Okay. You guys are all smart people. You all did really good in school. That's why you're in grad school. So you understand this is like math, right? As you go along and learn things in math, you got to learn the basic concepts. If you don't understand something along the way, you're done for. You're not going to catch up. So make sure you ask me a question as we go. Okay. So now you tell me, now let's identify these suckers here that are between the UU, these guys. Okay. So how are we gonna, what's the command gonna look like? So let's copy this and paste it. So first of all, the ones that we find are, we're gonna give them that label called UU. Okay. It's again going to be in that same slot, the pair slot. We're trying to fill up that slot with these things, LL, UU, etc. So now it's going to be, there's going to be one change to this remaining line. What's the change going to be?
Changing L to U.
Boom. I think that's right. Let's run it, see what happens. Group UU assigned to less of them. Let's see if we got it. Whoa, getting crazy here. Let's see if I can keep my head from exploding. Okay, here we go. LL is this red. UU is the purple. And then none. We still have, so notice the interface ones, right? And the facet ones, these ones here. So let's see. Let's look here. LL. Yeah, because blue is LL. Yeah, is L. So I think we got it. Let's look. Oh, what the hell's going on here? This guy is between UU, and he should be purple, and he is. Okay. You with me? So we got that so far. But we still now got these interface guys. What's the label we want to put on these interface guys?
LU?
Exactly. We want those to say LU. So let's go back here. So LU, here we go. This is, we want this to be LU. There we go. Now we're going to have to tell it both sides, because both sides are going to be different. Remember, every contact has two sides. So one of, if the guy on one side, doesn't matter which, if the guy on one side is part of group L, that's good. And now the other side, so somehow we got some crazy syntax. If the other guy is U in slot layer, this is what we want. And I think, yeah, and we got to say this. We got to say right here. So on one side, group L slot layer. So one side is L, and I want to say match one, just one side. And then the other one is U, and I want to match one. I don't like this syntax. I find it very confusing, but nonetheless, that's what the PFC developers did. So this is the syntax. So notice L, you match one. One side is supposed to say L, and the other side is supposed to say U. And let's see if this thing is going to work.
Oh, you need a space after the match first.
Oh,
Second
thank you.
match.
Boom. Nice. Run this. Well, it did something. 94. Let's see. Oh, I'm liking this. Okay, so let's start down here. These guys with the walls, they should be none, because we haven't found them yet. So they're none. That's good. Let's turn them off. Over here, let's turn off the none. Oh, wait, let's just make sure. And all of the wall guys are this none. So shut that off. Boom. Now, did we catch these interface guys? I think we did. So in this case, the blue and the white kind of are supposed to be LU, orange. And look at that. They're magically tracing along. and they're magically tracing along, right? So we have just done the first part of Shang-Di He's PhD work, right? And we did it with 6 lines of code, okay? Let's just do one more thing, and then we will take our break here. Now that we have this information and we have grouped all these things, now we basically have all the information we need to do all this, to assign properties and stuff, right? And so, for example, in this model, we have the linear contact model everywhere because we said CMAT, default model linear, okay? Let's just see, by the way, if that's what we have. So this is the model right now. If I go into model state, it says, oh, there's 1046 oh, look, there's one called contact CMAT. Holy crap, what's that? Oh, there's a default contact model, and it has the one called linear. That's what we're supposed to put in there. And it has properties. Oh, what are they? Oh, and here's all the different properties. There we go. KN, 1E6, KS, 1E6, frick. Where's frick? 0.5. There's other default values. So this is showing us, okay, and is that what we did? 1E6, 1E6.5, boom. So this is actually very useful when you start doing complicated things because it's telling you, is it doing what I thought? So this model only has one thing. It's the default, right? So let's just see if we can make the friction at the interfaces equal to 0. So we want to make this fric value just for the contacts at the interfaces to be 0. Okay. So now that we have all this information, we should be able to do that in one command. So let's see this. First, let's see what we have now. So we can actually plot and color the contacts based on certain values, like based on their property. And so let's first look at the property of fric in every single contact. And right now it should be 0.5 everywhere. So let's make another plot item. That's another contact plot item. Let's turn off this one. Turn off this one. Here's our new one. Let's make this thing a sphere. So there, just showing contacts. Now color by numeric value fric. Boom. There it is. Blue, 0.5. So every single contact in the model here has a fric of 0.5. And what we're going to try to do is just make the guys that are LU. So it's so fun. I feel like I'm playing a video game. I'll turn off the LLs and those guys. We just want those guys to have a fric of 0 and the other guys not affected. So you know how to do this. Watch. Contact property. Let's just see if it works. Let's just put contact property 0.42 for every single guy in the model and make sure that works. Boom. Property fric. There it was, 1046. Let's see. My view. And I want to look at the contact plot item, color by fric. Notice everybody is now 0.42. That command did it. So how am I going to modify that command? We're going to limit it to only apply to some guys. Which guys? The guys that have an L and a U on each side, right?
Yes.
And those guys are a group called LU. So I think, let's try this, range group L-U, and we want it to say LU in the slot called layer because that's where we put LU in the slot layer. Remember? Sorry, it's not the slot layer. It's the slot called pair. There. So if this works, it's going to say, okay, apply this command. And we're applying the command to contacts. That's why it starts with the word contact. Do something to contacts. And only do it to the ones that have a group designation of LU. So let's see if this works. Boom. Ooh, it just did 94. That's a good sign. Maybe it worked. Let's see. Let's shut all that down. Boom. So value, contact fric, numeric value fric, color opt. Let's do just named. And now I think we got it. Let's just change these 0.42, the 0.5 ones, make those be blue. Now let's see if it worked. It looks like it worked. 0.42, just these reds. Let's turn on the balls and make sure it's what we thought. I got a bad choice of color for fric. Let's make that color be yellow. There. So the yellow guys should be between the different colors. It looks like they are. Okay, there we go. So notice, and we do the same thing, right? We can use the other designators of LU, LL. So now we can give different properties to different parts of the model, okay? And so this is the whole thing, right? This is the idea, right? So the only thing different that Chengdi did is identified these balls based on overlaying the scan data on top of the system. And he didn't use a range. He basically wrote a fish function. He looped through every single ball and he asked the ball what its position is. And then he compared that with his overlaid scan. And he has an algorithm that says, given this position and given a scan, I can tell you which part of the scan I'm in. And then once he knew that, he could give a designator, you know, like Micah or something like that, right? That's what he did. Everything else, then, he just used that information with this kind of a stuff. Once you know the ball grouping, now you can figure out the contact stuff. And then once he had that, he just gives different properties. Now he's crazy. He's got 104. He's got all these different combinations, right? He had 3. He had a 3x3. He had 6 different combinations of what to do. Okay. Are there any questions?
Oh, I have a question
Go for it.
about this command works only for the exist contacts, or when there's a new contact generated during the calculation, it will be set like a new friction, or just default as we used in CMAT before.
Okay. You asked the awesome question. It's almost as though we had this, like I wanted you to ask that. Yeah, let's cover that. This is the last part of this. So Shihong is asking, what's going to happen now when I continue to run the model if new contacts form? And in the world of PFC, whenever a contact forms, it goes to the CMAT. And whatever the CMAT says, that's what it's going to do. And currently, the CMAT only has a default answer. And the CMAT says, I don't care. Any new contact that forms, put in linear model and give it these properties. So right now, the CMAT doesn't know anything about all this information because we haven't told it that. Okay. So let's just do this one time here. So let's say this system now, if we start deforming things and moving things, like for example, this guy starts getting pushed and these two contacts are going to disappear. That's fine. They're just gone. But now let's say this guy pushes into that guy. So then a new contact has formed and we can say, oh, we want to tell the CMAT that if a contact between those two guys forms, here's the property you could do it. Okay, so we can't use the group designators for existing contacts because these are going to be new contacts. So we're going to have to use the range logic. So we're going to say, for example, contact. We're going to say contact CMAT. We're going to add something to the CMAT. So we're going to say contact CMAT. We're going to add an entry. So we give the word add. Right now, there's only one entry in the CMAT. There you go. It's the default entry. But we're going to add a new slot to that. So we're going to add a slot. And in that slot, we're going to say, we want to give the model, let's just to keep it simple, the model is going to be linear and the properties, let's say, are 1E6, 1E5, 0.12. And that's not right because I got to say KN and I got to say KS and I got to say fric. Okay. But now I need to tell it, and I'm going to use the range logic. So then I'm going to say, stop there, range. Range, going to use the same concept. Range group right here. No, wait. Hold on. Yeah, that's correct. Okay, hold on. Let's make it as simple as possible. Let's say, what if it's just we want to handle the case where, oh no, let's do that one. Okay, sorry. We want to handle the case between a L and a U. This is the range that handles that. Look at this range. This says, remember, this is applying to a contact, and what it's saying is, this new contact forms. It always has two guys. If the guy on one side has the group L in it, and if the guy in the other has the word U in it, that means I've just fully defined those guys. It's only those guys. And if it doesn't satisfy this, it's going to use the default thing. Okay. So this is what we would do. Does that make sense, Shihong?
Yeah, I understand. So
Okay.
the contact property, this command would not be used for the new formed contacts, but the contact CMAT can do that, right?
Yes, this is a
Okay.
command that only applies to existing things in the model. And the CMAT is the magical thing that is going to allow you to tell it what to do for new guys that form.
Okay.
And
Thank
so you can see this gets pretty complicated when you start having multiple things, because now you would then need to sit there and say, right, all the possibilities. You need to now say, what happens when two blue guys come together? What happens when these guys come to, now there's like three possibilities, right? So this is the thing, right? So this also makes PFC completely general and powerful. I'm almost 100% sure no other existing discrete element code could let you do something this complicated. And it's totally flexible, right? I could have anything I want here. Like one of the things people have done is they model like a big pile sticking through here, and that's a bunch of different balls. And then it, depending at the interface, it's different. You get the idea. So this in general is what you need to do. Color the balls. You might want to put contacts in groups so you can visualize stuff, and then using that information, assign properties. And then also, if the model is going to have large strain and new contacts are going to form, you have to handle that case too to tell it what to do. And in a lot of times, you don't care about any of this and you just use the default. But now that we're starting to designate different types of regions and different types of materials, now we have to handle all these different cases.
Yeah.
Okay, we
Yeah.
good? Makes sense? And so the last
Makes
thing,
sense.
and then we'll take this break. Go ahead. Yes.
No. Makes sense. Totally makes sense.
Okay. The last thing is, see this. So then this is, I still can't believe I get paid for this. This company in Thailand, paid me $15,000 to do just that, to build a model. Basically, to build the model we just built. Rain down particles, let them settle, boom, define layers. The only thing left is take this wall take this wall that's black and this wall that's black and make them both have a certain velocity, and none of the other walls move. And then when you do that, you can see this behavior occurring, right? So this is, this is an example, right? This is like a simple example. And what I did is I made it so that there's separate properties inside the L and different ones inside the U and different ones at these interfaces. And in their world, they also make a bottom layer of weird stuff. And so I had to handle all three of these possibilities. But you can see how I did it. I just did it with these small number of commands. But I had to do what Shihong talked about, is what to do when you start having giant large strain, because new guys come together and what are they supposed to do? So, okay.
Yes, I can see.
So this is a good chance for me to make an invitation to Ayat. If you would like, it would be great if you could give a short description of your research at the beginning of the next lecture, with a focus on this odometer test and why it matters. Would you be willing to do that?
Yeah, that would be great.
Fantastic. Okay. Yeah, like 15 minutes or less. That sound good?
Yes.
Or less. It doesn't have to be 15 minutes. Yeah, just tell us about this. This is like a real world example of like real research. Like, what is it? Why do we care? Why are you doing this? How does an odometer test useful to you? Okay. And you can talk about the direct shear test too, because there's limitations to the odometer test, right?
Yes.
Okay. Thank you. Fantastic. Remember, you other guys are going to get on the line too as we go on forward, but I know Ayat and Shihang the best, so I can ask them first. Okay, PFC. Go back to the gravity pack. Let's just look at this thing. I'm going to look at the view. I'm going to restore that gravity pack. And so I'm going to double click on gravity pack, restore. Boom. Now we've got, these, the contact friction is 0.5, because that's what we told it to be, right? So let's get rid of these plot items. And we're just going to look at this. There's no more groups in there. So let's just look at the balls, make them yellow. Here's our thing we've been playing with, right? Okay. So what do we have to do to turn this into an odometer test? Tell me in words. Somebody.
Should it be me?
Sure.
So first we need to generate a platen or a top wall, and then we apply a force on that wall to compress the sample or the particles here. I keep saying particles, I mean the balls.
No, they're particles. Let's be a little careful. We apply a force to the wall. Is that what we're supposed to apply to the wall?
We're applying stress.
We're applying stress to the assembly. What is it when you run your odometer test? What is it that you're actually telling it to do, the system?
I'm telling the platen to move in a certain speed. So that's, well, in Word of PFC, it's velocity, but in the lab, what we did was strain control conditions.
Got it. So in PFC, what we want to do is make a wall, and we're going to call it platen, and we're going to give it a velocity in the negative y direction, and it's going to push against this, right?
Yes.
So that's the first thing we're going to do. And then the first thing we're going to do is we're going to take a history of the force acting on that platen wall. And so we're going to have, then we'll be able to view that history, and we'll see force versus step number. But we would like to see stress, first of all. So we're going to take that force, and we're going to divide it by the cross-sectional area of that platen, and we're going to call that an axial stress. And then we're going to plot the axial stress versus step number. Okay, you with me?
Yes.
So now we've got axial stress versus step number, but what we really want is we want axial stress versus strain. So then we're going to also monitor the amount of motion of that flattened wall. We're going to track that. We'll call it a displacement. And then we will be able to take a history of the displacement. So now we'll be able to plot axial stress versus axial displacement. And then, but we really want axial stress. So then we're going to, axial strain, I mean. And so then we're going to figure out how to turn the displacement into a strain for this system. And then that's what we're going to plot, right?
Yes.
Okay, so this is the plan. Okay, and you guys already know everything about doing this. There's nothing new here. Okay, so let's just leave this data file just like it is, because this is doing gravity packed. That's what it says. One thing along the way here, you should always have some sort of comments. So the top of this, create a cloud of particles allowed to settle under gravity to reach stable pile. Good enough. That's what this is doing, right? Let's say cloud of particles above a box allowed to settle under gravity to reach a stable pile. I cannot stress enough, when you're working with PFC, you're really being a programmer, because it's all scripts. And even if you're not using fish, you're still creating scripts. And so you need to practice basic things that programmers do. And they do these things because over decades of programming, there are certain practices that have been shown to be very important and very helpful. And one of those is documenting the code that you write. And there's all kinds of issues about documenting, because the key element then is how detailed does it need to be. And the level of detail really relates to who is going to be working with it down the road. And if it's just you, which in your case, that's mostly what this will be, it needs to be sufficiently documented so that when you come back to this 6 months later, having not even thought about it in that period, you need to be able to reestablish in your mind what's going on. I like to think of it that way, because I guarantee you're not going to remember all of these details. And then the additional amount, like for me, because I am an expert at PFC, this is probably enough for me to know what's going on here. And this is also a very small data file. But depending upon that, you should, put more documentation maybe, right? And so, that could be things like here, where you're making this history now, monitor porosity and force on bottom wall, right? So there we go. This little chunk here is doing that, right? I'm putting spaces in certain reasonable places. Here's a chunk of stuff. Then there might be a space between it, right? This all seems pedantic, and there are some people who don't document code. The expert programmer who's been with Itasca for as long as me, 38 years, who's written the basis of all the Itasca codes, he does not write very much documentation. He's kind of crazy. He's a unique guy. He also, if you go and talk about a theoretical matter with him, never writes pictures on the board. He does everything in his head. And so he's a very unique guy. And as a result, it's very hard for all of us at other programmers at Itasca to work with his 1 million lines of code, because they're not fully documented. So enough said about that. Put some documentation in, and when we start to write fish functions, you'll see we'll talk about other things along the way, like indentation and things of that sort. Okay.
Dr. Potyondy.
Yes.
It's a silly comment, but I will make it. Last
Please.
time when I sent you my code and you to review, and you wrote for me in the code to, how to document, and gave me suggestions. And since then, every time I'm like modifying the code or adding something, I feel like you're watching me, so I have to document the code properly.
All right, I love that. I love that. Yes. So the other thing we're going to do here, thank you for sharing that. The other thing we're going to do here is, okay, now what we could do is we could just hack this. That's like a programmer word, hack. You just like put something really gross really fast, and you need to go back and clean it up. We're not going to do that. We're going to do this properly. So let's just think about one level of something that's proper here. So first thing, we're going to have another data file. We're going to have multiple steps here. Make a gravity pack, perform an odometer test. Okay. Let me get rid of this. Remove layers. Okay. Or create layers. Okay. So let's go back here and let me find where we are. PFC tutorials, gravity pack. I'm just going to make a copy of this directory so I don't lose it. And I'm going to get rid of that make layers. I want to keep this as simple as totally simple, right? And in fact, notice the way I work, there's a gravity pack tutorial and in there is a text file. And this is actually the notes about all the lectures and what we're doing. And in fact, you should be aware of this because when you look at this and do it yourself, it would be helpful for you to look back at this, you know, now we're doing this right there. That's what we did, add colored layers. Okay, so now we're going to want to have a gravity pack data file. We're going to want to have a make odometer test data file. And if you think about it, what we really want then also is when this is all done, we want to be able to have one master data file that's going to do all. So that when this is all done, we're going to be able to just call one data file that's then going to make the gravity pack and make the odometer test. And then we might have a third one that's like run the test. Okay, so let's do that. So I'm going to say new data file, and I'm going to call this doall.p2dvr. Okay, someone dropped off there. Let's see. Admit all. How do I do that? It doesn't allow. Is everyone here still? Maybe that was just another. I think everyone's here. Okay. I just heard some beep in the background. PFC. Do all. So all the time, program return goes at the end. And so this is going to call, it's, how do I do this? Program call and file name, gravity pack.p2dat. Then it's going to call, what are we going to call this thing? Let's call it make odometer. Yeah, that'll be good enough. Make odometer, right? Okay, and so gravity pack is going to run. Here it is, model new, starts from scratch, makes a save file. So then when I call make odometer, it's going to restore that save file and continue on. That's how these things are going to work. Okay. So yeah, and this guy is called doall.p2dvr. Okay. Let me just make a comment here. Up until about 3-4 years ago, everything at Itasca, all the fish functions we ever wrote to do things, I think I call them like environments. Here's what environment to build odometers and stuff. We used to call this thing master.dat. And that was like the master, and it like controls everything else. And, you know, it turns out that at least in the United States, there's been a big, long history of racism against African-American people, and they were slaves in the 1800s. And so when you were a slave, you had a master. And so it's kind of out of respect for that, we try not to use the word master anymore. And so that's what we call this thing do all. So, okay, make odometer. So file, new data file, make odometer.p2dat. Boom. There it is. Program return. First thing we're going to do is restore. Model restore gravity pack.p2 save. Let's see if that worked. Boom. Error opening. It says it's not there. And that's because it's not there. I assume. It is there. No, it's not there because we haven't run the. So let's run the whole thing, the do all. So boom. So now it's running Gravity Pack. And you can see it says saved states and there's a line through it. That saved state used to be in the project, but now it's not existing on the file. So we're running it now, right? And this is a very typical thing as PFC. You do things in stages. So here we go. Letting this thing run. And it's always kind of boring when you're staring at a computer screen. And there's a thing people talk, a phrase we use in the United States sometimes. We say, this is about as exciting as watching paint dry. This is about as exciting as watching paint dry. And I actually did some work where we were modeling, not the drying of paint, but the drying of a mud flat in a lake bottom. And when a mud flat dries, it forms these hexagonal fractures. Looks like a bunch of stop signs. So then I would say I've actually modeled clay drying, not paint drying. Okay, enough said. I'm going to get rid of this make layers. I'm going to save this project, save project. So now the project doesn't know about make layers anymore because that doesn't exist anymore. We don't care about that. So make odometer. There we go. Run it. Boom. Ready to go. Let's do this. Let's give it a title that makes sense. I don't know, just for now. Odometer is being made. Boom. In fact, it's called make odometer. Let's just call it making odometer. ... Now run this. Make sure it's there. Making odometer. Makes me happy. Okay. Step by step. Okay. What are we going to do? We got to create that wall, right? So we're going to say, do one command, wall create. Okay. It's a pain to make one wall. Oh, wait, before we do this. Okay, so here, I talked about making a hack. Just think about this. When we make this wall now, we're going to give a command and we're going to have to decide on a height and we're going to have to give a position. Like, where do we make the wall? This way, we got to give it a number, right? Now, and you know, this was 0, 0 up here. So, you know, we're going to have to be minus, I don't know, 0.5 or something in the y direction. That's going to be gross because then we're going to have this crazy number, minus 0.5 in here. And if we go back and all we do is like change the position of the box or some small thing, everything will break. This won't work anymore. Okay. So what we want to do is create parameters for the fundamental things in our model so that we can set those parameters once and then we know what they are. And then we can use them when we do things like this. Okay. So let's parameterize this thing. Okay. And so what do we got going on here? We got this thing sitting at, let's do this. So way at the top here, create cloud of particles, parameters. Let's just do a few, sort of the most fundamental ones. So the box, it's going to have a width and a height, right? Let's do that. And then let's use that down here when we generate it. Okay. And so now we need to have, this is a variable as far as programming goes. So we need to have a name for the variable so we can then use it later. So we never want to use a one character variable name. It's not a good practice. It's too confusing and easy to mess things up with one. So let's just go in here. We could just do this with a box, height, and this could be the name, height of box, right? Let's start with that. These are our parameters. So these are going to be global variables in the world of fish. And so let's go and let's actually do this. Let's actually do this properly. What I could do here then is I could say global width equals 1 meter. Height equals 2 meters. For example, let's just do that first this way. So then I'm going to say model domain, and actually so what we should do, and we're not going to spend time right now. In fact, I'm going to ask that you properly parameterize this thing as a little exercise in the coming week. But I'll just do the kind of fundamental parts of it. So clearly the domain, so now we have to decide where the coordinate system is relative to the box we're going to make, right? And so let's do it so that the XY coordinate, that the box is centered on the 0, 0. Okay. And so that means that we're going to have this 0, 0 point, and then we're going to have a box. It's going to be 1 meter. And so we need a domain that's bigger than that. So let's make the domain like double that. So the coordinates for the domain, it's going to go from, let's say, minus width minus 2.0 times width. And in the world of fish, if we want to evaluate a fish thing, we got to use these crazy square brackets. And it's going to go to 2.0 times width. So that's that first part, right? That's the X min and X max. And then we got to give a Y min and a Y max. So let's just go and see how this works. Let's do height. Is everybody with me about this coordinate system being in the center?
Yes.
Okay. How do you spell height? Oh my God. H-E-I-G-H-T. I have such great respect for you guys from China because I have trouble with spelling of things, and I'm a Native American. I'm an American, right? It's got to be so difficult to do science in a language that is not your native language. Let's just run this, see if it works. Boom. Okay, it did something. Let's look at the view. There's no balls, there's a domain. So we should look at the domain and the axes here. Oh, boom. It's looking good. Let's change the height to be 1 and make sure it really worked. Height's 1, run it again. Oh, boom. I think we got it. Okay. So that's good. We're not going to parameterize the parameters of the linear contact model, but that would be an obvious thing to do as well. Because once you've parameterized it, all you're going to do to make a change is just change these values of the parameters, right? Let's now generate this box. So, copy, paste. So, okay. Yeah, so we got this. Help me do this. So let's look at it. We want, that's the domain. We want the box to be a height and a width. So we want to go, the width, we want to go negative half the width and positive half the width. That'll give the width, the actual width, right? So we want to go from A to B, C to D. So what's A? Some value, evaluate it, minus 0.5 times width and plus 0.5 times width. And then we're going to do the same thing for the height. So this becomes height. Height. There we go. Spelling is an interesting thing. My wife is a lawyer, She works for the Minnesota Supreme Court. She's an extremely smart person. She couldn't spell if her life depended on it. She writes big, giant legal documents for the court, and she just cannot spell. Okay. Here, let's run this. See if we got it. Boom. Mismatch parentheses. This is why I do things step by step. Does anybody see what's wrong with this?
Yes.
The second
So the
width.
second width, you don't have
Sorry?
the square bracket.
There.
Should be fine. Yes.
There you go. So now let's look at it. And now we have to turn on the walls. So we turn on the walls. Ooh, and I think I might have it here. Let's make these walls black. Color option, black. Turn off the axes. There we go. So far so good. Let's go back. So get rid of that command. And we're going to delete the top, just like before. Let's hit a return and see if that works. Boom. That's looking good. Let's turn off my domain now. We're not going to worry about that anymore. Okay. Now, we just got to do the generate command. And we got it. We want to parameterize. Now, let's see. So, comment out that one. So, ball generate box. And in this case, let's just go here and put the cloud of particles directly in the place where the box is. And make them with no overlap, and then let them settle. So they'll be a little bit below the box. So that means we can use this exact same box command. That makes sense? Okay. And now we need to give the radius range, A to B, and this thing that's number thing. Remember, when you actually are doing this, you would be using the distribute command. So you wouldn't be giving a number. It would be much more general. You would be giving a volume fraction of guys of a certain size. And then along with that, you'd be giving a cloud porosity, which is in the end then going to control how many you get from that size distribution. But we're just going to keep it like this. And so radius, right? So let's at least put that in there. Global. And it's a uniform distribution. So let's say R min equals, what did we use before there? Help me. 0.03. 0.03. Whoops. Hit the wrong key. I'm trying to copy and paste. R min, R max. And what did we use before? 0.04. Let's not do it. You guys can clean this stuff up later. So here we go. Radius is going to go. I got to put those crazy square brackets because it means evaluate a global variable. So this is R min. This is R max. 500. Return, run. That's what we expected. 121 balls were generated. Now turn on the ball plot item. There we go. Let's make them a little smaller. 0.02. Run this. Let's just live with that for now. 153, right? Well, this is kind of cool, right? Because we're going to develop this whole thing and make it work with this small trivial model. And then everything will work. All we have to do is change this number and change this number. And we can then make a big giant system with a whole bunch of smaller particles, right? Okay. Is everyone with me?
Yes.
Yes.
No?
Yes.
Yes.
And for this guy, we're just trying to make a huge number. We're just going to put that freaking thing at 1 million because what we're doing is we're just generating this size distribution and it's trying to do it without letting them overlap. So it's going to tell us that fewer were generated based on how much fit in there without overlapping. So let's just put that number giant. So we don't have to really think of that as a parameter anymore. Okay. So there's our box. And what else? The ball density, again, we'll just leave that as 1,000. Damping, gravity, no problem. We're probably not going to make this work on the moon, so we'll just hard code in. Oh, what about units, right? This data file, no one has any idea, so what I like to always do, here's my parameters. They're going to follow here. I should specify what units you're using. So there we go. I always use that. SI units. So now these things make sense. Okay. Now, and actually, let's not put any of this stuff in here. We're not going to monitor histories of the wall and all that stuff. We're going to make this super straightforward. This should be enough. Oh, notice here I said meters per second squared. That's because I didn't say SI. Well, actually, yeah, here we go. I'm using SI units everywhere. That's what I'm saying. Okay, let's run this. And let's look at the contact force chains so we can see what's going on. And let's stop it. Remember, after we generated the balls, let's put a pause here. Because remember that, so this generate is putting them. Try again. Boom, I double clicked it too fast. So we're generating them in the box, and now we're letting them simply settle. So they're going to be lower. So like when we make our platen, we might want to make it here, we might want to make it lower down. And then here we're just going to get to equilibrium, right? Okay. Now, let's talk about programming practice again here. So get rid of this pause. Everybody's good here. And to make things even
Yes.
simpler, let's get rid of this size distribution business. That was the one that was measuring the size distribution. And it was coming from this PF's particle size distribution. We're not going to use that to make this. I'm trying to make this as simple as possible. Save project. There we go. Okay, a couple things. I'll take out the kilograms per cubic meter to make it even simpler. Okay. Save, here's what you should also be doing. Save the project. Shut the thing down. Make sure that you can start it up and everything's okay. This is part of this developing things step by step. Just take a few steps, make sure it works. Everything's okay. It should have restored everything. It looks good. We should probably be okay. Now, think about this. When we're done with this whole thing, I think of this as an environment, right? We can now go and just call this thing gravity pack, and it will run, and it'll run this data file, and this data file, we've kind of hard-coded in these parameters, which means that if we run this again, we have to change this part of the data file. Now, it might be, this is a very common thing. You basically have a set of parameters that control things. And to make this even another level of generality is you would want to put the parameters just in one file. Okay. And so that way, then you have a file called my parameters. And then whenever you want to change things, all you do is change that file, and everybody else refers to it. So let's do that. So let's say make a new file, data file. I'll call it my params.p2dat. Program return. And so in there, I'm going to take this and copy it. Go to here. Here we go. And so now that description of the parameters should be going in there as well, right? So I'm going to copy that. I'll get rid of these in a minute. Whoops, Control V, boom. So here we go, right? Oh, and I didn't say what this is. R min, R max, in minimum and maximum radii for uniform distribution. right? And there's two of those things. So it's a group of things. So there you go, curly braces. I don't know. And then there's all kinds of craziness if you want to like, I find it helpful to keep these things lined up. So now I've got a data file with parameters, but now this guy has to know about that. So here I'm going to say program call my params.p2dat. And now I can get rid of, wait, get those SI unit business in there. SI units, right? Program call. So now I should be able to get rid of this. Should be able to get rid of this. Now let's run this guy, see if it worked. And I think it probably worked. Okay. So you see the idea here. This data file is finished. I'm done. I never need to change it again, ever, unless I want to add more functionality. Okay. Like maybe this random seed probably should be a parameter as well. And then you put that in here. So now whenever I want to use this environment, I know that all I'm going to do is change the stuff in here, the parameters. Okay. This is a very, very helpful way if you do even this is quite a trivial thing. Already there's these different levels of organization that are very helpful to do. So this is the way you should be doing stuff, is by creating parameters and then using them and setting them in one place is kind of an ideal way to do this. Okay. So run this, and now let's see if we can use those parameters and make this odometer test in the last few minutes here. There we go. So let's make the platen wall. Let's just put it up here because it's easy. Because we don't really know how far it is to be down here. Let's just put it up here. It's just like a real platen sitting at the top of the cell. And then we're just going to start moving it, and eventually it's going to come in contact, right? So make odometer. Model title, making odometer, run this, restore, making odometer. Is it there? It is there. Good. So wall create. Now we're up to wall create. Wall create. How do I create a single wall? It's kind of a pain. I don't think I have the ability to just make a single. Oh yeah. Wall generate. Can I make like a straight line? I don't think so. I can make I can make a line. Generate a line wall. 2 facets. That's what I want. Okay. Wall generate line. I have to give position of the 2 endpoints. The hell is this? Oh, this is for 3D if it's out of thickness, out of plane. So wall generate. So it's going to be wall generate line something else. See if this works. Wall generate line, and then I need to give the word position. Then I need to give A and B. So the position is going to be what? So we want it to go from, turn on the axes, make that smaller, turn off the balls, turn off those. There we go. That's 0, 0. This point is 1/2 width, and this y coordinate is 1/2 height, right? And this one's minus that. So let's try to do that. Let's go. So this something, this is going to be something. So this is going to be x coordinate minus 0.5 times width. And then the other end is going to be plus 0.5 times width. Wait, this is not right. Hold on. Oh, okay. Position goes from A to B. This is just the x coordinate. So the position, x coordinate, y coordinate, x coordinate, y coordinate. You with me? That's what it's expecting. Notice position, V1, V2, V, that means a vector. Vector in 2D or 3D, right? It has to have 2 numbers in 2D. So So the y coordinate, what's the y coordinate? Ling, what's the y coordinate? You're looking for this right there, that point. So this is 0. This is h, height. So it's going to be plus 1/2 height. And this will have the same. So plus 1/2 height. And this will be the same thing. Run it. Come on. Unused extra parameter. What the hell? Okay, help me. Wall generate line position. Let's go to the command. Whoops, that's not the command. Let's go back. Come on, get me. There we go. Let's look at this. Wall generate line. So far, so good. After line, you say position, boom, boom. Okay. Oh, this, okay, what? Here we go. V is a vector. Okay. A vector is a certain fish type. And so let's do it. Let's do it this way to make it clear. Global point A equals a vector that has a x and a y coordinate. Watch, you'll see this in a minute. Here we go. Let's cut that out of there. And this is going to be point A. Point A is a vector that has a height and a width. Let's just run that. Syntax error, help me here. Vector. Let's see. Syntax error, vector.
The height.
Okay, help me.
Height.
Thank you. Maybe it's just that. Still not
And,
happy.
The
Here's how I
bracket.
debug this thing. Let's just see if that works. Let's see if that works. Okay, that worked.
We should the bracket, the square bracket. Should we use that in fish syntax?
No, we shouldn't. Okay, hang on. Width, height, copy, vector. Watch this. How? Now get rid of these square brackets because now it's inside of it's evaluating a fish function, so it knows about fish variables. So I need the brackets out here, these brackets. But inside the brackets, you're in the world of fish. So this is just a fish variable. Let's see. Looks good. Let's say list fish. There we go. Point A is a two-dimensional vector, and it has those values. Okay. There's also way over here a little fish symbol. Here we go. Here's the name of every fish variable. Here's the value it has, and here's the type. So point A is of type vector2. It has those values. I'm sorry, I can't make this bigger. So this means we do this. So point A is that. Let's call it point B is going to be, this is going to be height, right? I replace width. No, I do width. It's this, whatever this is. Yeah. Yes, it's what we had before. Let's do that. Get rid of these. If things are logically related, it's very helpful to line them up because you can see then in the format what is the logical relationship between things. Point A, point B. Let's do this. Return, let's do list fish, and then return. Let's see if those are what we think they are. There, point A, point B. I think we're good. Let's get rid of that. Let's do the command. Okay, what's wrong? Okay, let's figure this out. Unused extra parameter 3. Extra parameter 3, line. Oh, That might be a 3D only. I said wall generate question mark. There's no it doesn't support the word line. Let's look at the documentation more carefully. And I bet it's going to tell us that. No, look at that horrible thing. It says 3D only. Okay.
Yeah.
That's why this is a pain. So we can't use the generate command. We have to use the create command. And here we're going to give the word vertices. So let's do this and then we'll be done. Wall create vertices. Wall create command. Vertices. And then after vertices, we just give a list of them as vectors. Boom, boom, boom. Because, you know, a wall can be a whole bunch of vertices joined together, which is facets. This is just 2 facets. Let's see if this works. Oh, it created a wall. Let's see. Oh, boom. There it is. Wall, facet, text value, name. So look at the name. Bottom, left, and right. That's what we created with the box command. And then now, wall 5. Well, that's a stupid name. We want to name it. What should we name it? We've been talking about it as platen, so let's name it platen. I think that's the syntax. Wall platen, wall called platen. View. Bottom, left, right, platen. There we go. And so now we've got, let's make that platen red. Boom. So now we've got, and we might screw around and make the left and the right and all that stuff. Just make those all be black. Right. And so now it looks a little more clear. We've got the wall. Okay. And let's just do a quick thing here. Let's just make this wall move. So we're just going to say wall attribute. And one of the attributes of a wall is velocity. I think wall list attribute. Boom. Here they all are. Velocity. So I'm going to say wall attribute velocity minus 1 meter a second. I'm going to parameterize this, but right now let's just see if it's working. So go back to the console. So it gave it a value, that value. Now let's cycle. I have no idea if that value makes sense or not for this time step. There's the balls. Probably going to be too fast. Cycle 10. Oh, looks like it's a lot. I'm doing cycle a million. Oh, what's it doing? What the heck is it doing? Run it again. Wall attribute velocity.
Velocity in Y position.
I guess we didn't specify the range.
Both of you are correct. Since we didn't specify the range, if I do wall list attribute, oh, that's not what I want. I want to say, I want to see, oh, velocity. Yeah, wall list attribute velocity. Boom. Here's the walls. They all have the same velocity. And okay, so I don't want that. I only want to I want to limit it to the platens. And I also just want the Y velocity to be -1, not the X velocity. So I got to rephrase this. Wall velocity, this is looking for, I can do this as an XY, I think. No, I need to say velocity Y -1, range, set, name, platen. See if that works. It told me in one wall, and if I list, whoops, come on. There we go. They're all 0 except for the Y value of platen. So now if I run it, now I'm just going to cycle. Cycle 1 million. Boom. Here we go. It's going to slam into there. Go all crazy. Okay. And if we look at the force chains, make sure it's making sense. I lost my plotting tabs, but there's a little left arrow. Pulled it back. Contact forces. There we go. So let's do one last thing, and then we'll be done. My parameters. Let's make a parameter for the velocity. Platen. Oh, let's call it P-vel, Platen velocity, right? And so then up here, we're also going to do that, P-vel. And let's make it 10 times slower, equals minus 1.0 e to the minus 1. Okay? And we'll talk about next time, how do we figure out what to choose for this? And then we got to use that. So here, we use that value. And we're going to say minus P-vel. And let's be clear, P-vel is Platen velocity, positive number. It's really crazy if we assume the person has to know it's, that it's negative. So the parameter is very clear. This is the velocity of the platen. The model, has been set up to know about that. So that's why it's in the minus y direction. So if we run this, range set name plot, what did it do? Unrecognized word. Oh, I got to run it from the start because it's gravity pack. When I run this, that's when it's going to suck in the parameters. So do all. Let's watch. Oh yeah, here we go. Watch, it's going to pack and then it's going to call make things. So then it should make that wall on the top and then it should push that guy down. You can see it takes forever because it just keeps slowly settling here. Here we go. Oops. And here I didn't cycle. So let's just say cycle some big number. 50,000. But we're also going to have to think about down the road here, what are we going to do? We don't just want to say cycle freaking 50,000. Like, how do we know how far to go? We're going to think about that. Oh, look, it's going up. How come? Minus P-vel. Let's look at what P-vel is. P-vel that it has. Oh, P-vel. Yep. Okay, so the P-vel that I put in there, I put in as negative. It's always supposed to be positive. There we go. Now we got to run it. Da-da-da-da. So what I'm going to ask you guys to do actually is finish this. Okay? Make this odometer test work. Make it, see what you can do. Plot the histories of these things. Let's just make sure this thing is working here. So now it should come into contact. We should get new contacts forming. And we should get rearrangement as the particles respond to this thing. How does it know what type of contact model to put in? We made new contacts now. There we go. How does it know what contact model to put in?
The same mat.
CMAT, right? Let's look at that. Contact. Color by. Model name. Linear active. These are new guys, linear, because the CMAT was the default. The only thing we had was the default one, right? We go to model state. What's the contact CMAT? There's only one possibility. There's only one slot, the default slot, linear model, right? Okay. So we're going to stop here. Let me just put in a couple comments for you guys to do. So in fact, here they are. I'm going to, in this gravity pack, there's my little notes. I'm just going to say C. In gravity pack dot text, txt. There you go. Do it. See if you can figure this out. Okay. And you can look at this. When I send this to you, I'll rename this. I'm gonna keep this one. Call this original. Because the hint is in here. Because in the original, remember, we already kind of did this. You can look at that for reference where it says gravity pack here. Remember? Right there. here's the, right, we're going to look at the wall and we're going to look at the Y contact for it, right? And then we're going to create a fish variable so that we can do things like turn it into stress and strain, things like that, okay? That's all I'm going to say. I'll send you all this stuff as we've done. And with that, we'll be finished for today. Any questions? Okay.
Thank you.
Okay. And I know that's one last thing to say. This is why I'm so appreciative of you guys being in this course. This course is always taught much too fast. And I go so fast and it's people don't really keep up. I believe I've been going slow enough that you've all been coming with me and following things. I hope you're not bored, but I'm intentionally doing this very slow and step by step. Okay. So